Every single day, engineers make thousands of decisions that hold the world together. The concrete under your feet, the bridge you cross on your commute, the building where you live and work, all of it is the result of calculations, materials, and human judgment. But what happens when those decisions go wrong? When the math is close but not close enough, when the materials are cheap or the shortcuts are taken, you're about to see it. These aren't simulations. These aren't cartoons. These are real structures, real sites, and real consequences. And in almost every single case, what you're watching could have been prevented. This is Dallas, Texas. A brand new residential building under construction, wooden framing, multiple stories. And it didn't take a hurricane or an earthquake to bring it down. It took a storm. The problem isn't the weather. The problem is what engineers call lateral bracing. The diagonal supports that hold a structure rigid against sideways forces like wind. During construction, before walls and floors are fully in place, buildings are at their most vulnerable. Without proper temporary bracing, a strong gust of wind turns a frame into a deck of cards. This building came down because someone skipped a step, one step. And in engineering, you don't get to skip steps. Now look closely at this. What you're seeing here is what engineers call a water-cement ratio failure. This concrete is too dry. It's clumping, it's not flowing between the rebar, and it's leaving voids, invisible air pockets buried inside what's supposed to be a solid structure. Here's the terrifying part. From the outside, once it cures, it looks fine. There's no crack, no visible sign of weakness, but inside, the structural integrity is compromised. Those hidden voids concentrate stress. And when a storm hits, when water pressure builds, when wind loads increase, those invisible flaws become failure points. Bad concrete doesn't fail immediately, sometimes for years. This is what engineering looks like when it's done right. Hundreds of workers, precision cranes, massive precast concrete segments, all of it coordinated to build one of the most complex structures humans have ever attempted. A mountain-spanning highway viaduct. Projects like this require tolerances measured in millimeters across kilometers of structure. Every segment must match the next. Every pier must be perfectly vertical. Every joint must be sealed and load-bearing. And here's the reality. Even on a project this well-resourced, with this many engineers on site, failure is one bad decision away. Scale doesn't protect you. Attention to detail does. This is called a formwork collapse, and it is one of the most dangerous events in construction. Formwork is the temporary mold that holds wet concrete in place while it cures. It has to support enormous weight. Fresh concrete weighs over 150 pounds per cubic foot. When the formwork fails, it takes everything with it. The wet concrete, the rebar cage, the scaffolding, and anyone working nearby. Why does this happen? Overloading, improper shoring spacing, connections that weren't checked. In many cases, it happens because someone poured faster than the design allowed. Wet concrete generates pressure, and that pressure builds from the bottom up. The structure didn't fail. The system around the structure did. In engineering, the temporary is just as critical as the permanent. This retaining wall is in British Columbia, Canada, at an active urban excavation site. You can see the cracks, long, vertical, diagonal, spreading across what was supposed to be a solid concrete barrier, holding back tons of soil. Retaining walls fail for a few key reasons. Hydrostatic pressure from water building up behind the wall, inadequate drainage, insufficient anchor depth, or soil conditions that weren't accurately assessed during the geotechnical survey. When this wall goes, and at this stage it is going, everything behind it moves. Soil, groundwater, and anything built on that soil. One retaining wall is not just a retaining wall. It's the reason the building next to it stays standing. Here's a failure that's less about structural engineering and more about site engineering, the decisions made about how equipment is positioned on unstable ground. That excavator is working on a frozen embankment. The problem: frozen soil and thawed soil behave completely differently. Below the frost line, that slope may have already softened, and a fully loaded excavator can weigh 80,000 pounds. When the ground gives, there's no recovery. The machine goes wherever gravity takes it, in this case, toward a live highway. This is why geotechnical assessments aren't optional even for temporary operations. The ground doesn't care what your schedule says. This is what happens at the end of the chain. Every failure before this, the bad concrete, the skipped brace, the undetected void, eventually produces a moment like this. An elevated highway, fully built, simply tilts and comes apart. This type of failure is almost always the result of a foundation issue, a pier settlement, a scour failure beneath a footing, or a geotechnical condition that wasn't captured in the original soil study. Bridges and viaducts are designed with safety factors, typically 2 to 3 times the expected load. But those safety factors are only valid if the foundation assumptions are correct. When the ground beneath a pier moves even a few inches, the load redistribution across the entire structure can exceed design limits almost instantly. A structure that stood for decades can fail in seconds. This might look minor compared to a highway collapse, but look again. That is an entire concrete staircase, fully cast, now leaning at a dangerous angle inside an occupied construction site. Staircase failures in reinforced concrete usually trace back to one of 3 causes: inadequate connection to the main structural frame, premature stripping of the formwork before the concrete reached design strength, or rebar placement errors. Concrete reaches only about 70% of its design strength in the first 7 days. This scene is from South Asia, and it raises something important. Engineering standards are not the same everywhere. The bamboo scaffolding you're looking at is actually a centuries-old system. Bamboo has incredible tensile strength, and in many regions, it's the material of choice for temporary works. Every single collapse you've just watched has a paper trail, a set of drawings, a structural calculation, an inspection record, or the absence of one. Engineering failure is almost never a mystery. It's a decision that was made, reviewed, approved, and then forgotten until the moment it mattered. We build the world we live in out of concrete and steel and math and trust.